News from Cambridge Earth Sciences. Today we're heading over to Greenland and time travelling back to the first 50 million years of Earth's history, when our planet was just a mere toddler. The barren rocks that litter the landscape of southern Greenland might be covered in ice today, but they hail from a time when Earth's surface was a hellscape of incandescent magma. New research led by Cambridge Earth Sciences' Dr Helen Williams has identified the remnants of an ancient ocean of magma in 3.7 billion year old rocks from Greenland. I'm Erin Martin-Jones, and in this episode I catch up with Helen and find out how the team used forensic style analysis to track down the ancient ancestors of these rocks, and whether we might soon be finding more evidence of this distant and fiery phase of Earth's history on our planet's surface. Thanks, Helen, for joining me. So, can you explain why was the Earth almost entirely molten at this point in Earth's history?
So, the Earth and other planets grow through a series of collisions. So, if we think about our early solar nebula, it was likely to have been made up of a sort of a chaotic mixture of dust and rocky particles, and that this material would have coagulated together, forming small planetary bodies and then ultimately small planets. And it's collisions between these kind of planets, which is a process called accretion, that would have slowly allowed a large mass of material, that mass of material being the Earth, to have built up and grown. And these collisions can release enormous amounts of energy, especially when the planetary bodies colliding are very large. And it's actually been suggested that the Earth's moon is the product of a collision between the Earth and another planet roughly the same size as Mars. And so this is the event that we really thought would have given rise to nearly whole-scale melting of the Earth.
So this was also a kind of key stage in defining what makes our planet what it is today in terms of its habitability and atmosphere. Can you explain that a little bit more?
Sure. So I think one of the overwhelming kind of puzzles, if you want, in planetary chemistry and understanding the evolution of the Earth is, well, why does the Earth support an atmosphere, oceans, and life? When planets such as Mars, which are arguably formed from more volatile, rich material, do not. So there are many aspects to our planet's internal evolution and structure that we don't know. But what it appears is that this initially molten stage would have defined the internal structure of the Earth, may well have controlled through high-pressure mineral reactions the oxidation state of the Earth's mantle. And then in turn, everything is very much kind of holistic, but the Earth's atmosphere the chemical evolution of the Earth's atmosphere is linked to the chemical evolution of the Earth's interior through processes such as magmatic degassing. So ultimately, if you want to understand why the Earth has evolved to become a habitable planet, then you need to understand every aspect of the Earth's growth and evolution.
This is also going back a hugely long time, isn't it? This period in Earth's history was really when it was a kind of toddler in the first 50 million years.
Yeah, exactly. I mean, this is kind of going back to something that was sort of over 4 billion years ago. So it's kind of really going back into sort of deep, deep time, which we only have a very kind of blurry window into.
And as you're alluding to there, we don't know a huge amount at all about this distant phase of Earth's history. Why is that?
So the Earth is really unique in planets in our solar system in that it's got active plate tectonics. So that's the process where we create new oceanic crust at mid-ocean ridges, and we also destroy the surface of our planet at convergent plate boundaries, where one plate is pushed below another into the Earth's interior. And that means that our planet has really been resurfaced multiple times over its history. So we have very few areas of the planet where you have unmodified rock that's ancient. And then the other thing is that even if you do have ancient rock present at the Earth's surface has evolved through numerous episodes of kind of collision and mountain building and melting, and all of these processes impart their own chemical signature. So you've got to find ways of pulling apart those different types of chemical signature until you can see the signatures of the very early Earth processes you're trying to unravel.
So the evidence itself doesn't really exist at all because those rocks have been recycled, but then you've got to do some very detailed forensic kind of work to get back to that link.
Exactly. I mean, most rocks have been recycled, some rocks have not, but then exactly, you have to really spend a lot of time thinking about how you're going to unravel chemical clues for the early evolution of those samples.
So Greenland is obviously a really special place for geologists. In any case, they're some of the oldest rocks on Earth. But why did you decide to look in Greenland, and why are the rocks here so special?
So this particular region in Greenland is known as the supercrustal belt. And it's a region where you have very ancient rocks, but for whatever reason, it's what we call a relatively low strain zone. It hasn't accumulated a huge amount of deformation. So that means that you can look at these rocks, and although they've been metamorphosed and overprinted, they still preserve some of their original rock textures. So what attracted me to these samples was actually a prior study by one of my collaborators, Hanika Rizo, and she'd worked on these samples and she'd looked at chemical tracers for their origin, and there was just enough information in the data that she'd already acquired that suggested to me that these would be very suitable targets for the kind of project I wanted to do.
So what was it that piqued your interest about Hanika's work?
What was really interesting from Hanika's early work was that it suggested that these rocks came from a chemically unusual region of the Earth's interior. They were basaltic rocks, so to first appearance they would look like any other kind of basaltic rock you would find on the surface of the Earth, so nothing very special. But it was really the evidence of their chemistry, that they came from a different region of the Earth's mantle, that made me very excited in them. And then the question that I had to answer was, is the reason they've got a chemically anomalous source signature, if you like, was that related to these sort of very early magma ocean events? And I guess the attraction of working on really ancient rocks is because they've formed, well, comparatively close in time to those events, and obviously here we're comparatively close in time, is now 600 million years, so you have to change your definitions of time. But then it means, at least because these were formed by melting at such an old age, you have less time for their source region to become, affected by plate tectonics, affected by convective mixing. You've got a better chance of kind of getting back to that primordial signature.
So what was it about the chemistry of these rocks that really gave away their unusual history?
So the interesting thing for me was that they had decoupled neodymium and hafnium isotope systematics. It signaled to me that there was the possibility, and it was only a kind of a very hint of a possibility, that these rocks were derived from material that might have once been present at very high depths in the Earth, very great depths in the Earth's mantle. But I didn't know that for sure. It was just a hunch. It was a hypothesis to test with our data.
And you're also interested in the tungsten isotopes, and this is a very rare and dense metal in these rocks. Can you explain that a little bit more?
Yes, the tungsten actually was already published. That was also done by my collaborator Hanika, and that was a subsequent paper to the first one with the neodymium and hafnium work. And again, the tungsten was also very interesting to me. So really it was kind of this combination of the neodymium and the hafnium and the tungsten that made me think that these would be the perfect sample set to test out my idea on.
So a combination of those factors told you that the rocks contained both a hint of something old and something which had come from depth then?
Yeah, I mean, it's sort of a bit more complicated than that. But, the tungsten... the fact that you've got this tungsten anomaly really tells you that you had some process that created that source region that was operational in the first 50 million years of the Earth's history. So even if you don't know exactly what's happened, you know that region of the mantle experienced melting or other processes happening really early on. And then you've also got, from the combination of the neodymium and hafnium, this suggestion that may well have involved high pressure mantle phases.
So it was your work on the iron isotopes that brought this all together then and confirmed to you that the Ischios rocks contain remnants of this magma ocean. How were those remnants distilled into the rocks we see today in Greenland?
Yeah, the distillation is really referring to how you form those chemical and isotope signatures in the source region. And then, we know that at you must have brought some of this material up into the upper mantle. And there in the Ischios samples, you actually can see this mixing relationship where you can see that most of the Ischios samples have an isotope chemistry signature of normal ambient mantle. But there's a suggestion of a tiny amount of this really unusual mantle material being mixed in. And if you think about it a bit like, if you add a drop of very concentrated pigment into white paint, how you can actually see its chemical fingerprint, even if it's largely been mixed away. And that's really what we're looking at there.
So how did these rocks then find their way to the surface to be erupted in Greenland?
That's a good question, and we're not entirely sure, to be honest. I mean, certainly what we see in the chemistry of the Ischios rocks is we see that there's evidence for both melting of normal mantle material as well as melting of this very unusual mantle that's got this high pressure signal. So possible mechanisms could be something like a mantle plume, could be something like a thermal anomaly, or indeed very early plate tectonics, but we don't actually know.
So this is obviously really tantalising in terms of finding more of this evidence out there on Earth's surface. What's next in store for your research group?
Sure. So I guess one of the big questions that came out from this research, a question that we have, is was this just one tiny little snapshot that we were lucky to stumble upon? Or is this signature much more prevalent in both ancient rocks and even in modern samples? We don't know that yet very well, simply because no one has gone out and looked for it in the same kind of way. So I think the next stage in our research is to ask the question, if we go and look across numerous different ancient rock suites, do we see evidence for the same kind of source material present? How widespread is this signature? And I think that's the first thing to think about. And then I think the next thing would be to say, well, if we see this expressed to a greater or lesser extent in ancient samples, to what extent do we see this present in modern melting regimes? We know that there are mantle plumes that give rise to melts with distinct tungsten isotope compositions. No one really understands their origin. It's pretty much an enigma right now. So the next question would be, well, do those particularly strange chemical signatures, can they then be related to this magma ocean process?
So without giving the game away too much, do you have anywhere in particular lined up that you might be looking?
So what we're going to do first of all is just to look at really old continental cratons. So looking at really classic suites of very primitive melts called komatiites and ferropycrites. And many of these suites have been studied extensively before, so we've got a really wide network of collaborators and friends who were happy to share samples and sample localities. So we're going to work through these, so it's going to be a very big team effort with hopefully involving scientists across the world. And then, we'll take it from there after that.
Excellent. I think it's really exciting that there might be more evidence just waiting to be found.
Certainly it is.
So I hope you enjoyed hearing from Helen there. If you'd like to read more about this and other research from our department, then check out the news pages of our website at esc.cam.ac.uk. You can also follow us on Twitter at EarthSciCam, as well as on Instagram at Cambridge Earth Sciences. So until next time, stay tuned for more news from Cambridge Earth Sciences.